In this presentation, I'm presenting the novel productivity index that's been used for SAGD producers. And now it's modified for steam flashing effects. And we have two sort of models, they call it Coning 1 and Coning 2, that's been implemented. And we're going to discuss the effects. The importance of the modern liquid pool modeling and current timing is a lot of operators have been using FCDs, flow control devices, for their operations. And the problem is once we don't have a proper software to model these things, and we're not capturing all the phenomena, like going into the liquid pool, near-variable flashing, then we may come up to the wrong conclusions and wrong designs. And so this is the example of one producer that have FCDs, and we see after FCD deployment, now the plateau line moved to upper lift. So we have uplift here, everyone's happy. But the same asset, 2 or 3 wells on downside, we put FCD down there, and we see a negative effect. So no uplift, and the rates drop like crazy to half of the previous baseline. And this is as a result of operational constraints. FCD design includes the configuration of FCD and the type of restrictions we put there. And this all operational and FCD have to be modeled properly to capture the benefits of the flow control devices. And the basis is most current applications and softwares are really based on conventional world. And there's a huge difference between conventional and SAGD operation, and that relies on the steam trap control. That's most people talk about as subcool. In simple words, steam trap control is to mitigate the steam to come to the producer. And we have two range of a spectrum here. So green is good. So that's the time we put the right subcool here, and the liquid pool stays here and no steam comes in the producer. If you put large subcools, that means the liquid pool height is growing towards the injector, then you have the cases that you inject the steam into the liquid pool and you get shocking effects. So they call it injector flooding. And on the lower case of the spectrum, the subcool is pretty low. They start flashing close by the producer, or you have the producer go below the height of the liquid pool, and then you expose the producer to a steam, and you get huge steam coming too. Coming steam means production, pump failure, a lot of other concerns, scaling. So that's the case you don't want to happen in SAGD operation. To go and discuss this subcool thing, we have to explain the pH diagram, or pressure enthalpy diagram first. So this is a pressure diagram for water and steam. Every pure component has similar diagram with different numbering actually. So it's not unique about a steam. Every pure component has that. So in this case, we have a critical point and we have two lines. They're called water condensation line and a steam 100% line. That's what we call it here. In case of a steam chamber, inside a steam chamber, above the liquid pool, we are in this region. So we are at 0% quality to 100% quality, and we happen to be between these 2 points. And in these 2 points, changing between this quality thing, we're not changing pressure and temperature. The thing we change in the quality of the water, and that's correlated to enthalpy. But if we inject higher pressure or lower pressure, then this line is shifting. So you see if you go higher P, that means higher temperature, but at the same time, you have less latent heat. The length of this line is less than this. So this means latent heat is lower. That means it's easier to flash. But if you come lower P, you have a higher latent heat. That means you are less prone to flash. So now we understand the pH diagram. Let's discuss the subcool here. So this is the same diagram here for one case of injector and producer that happens to be inside the liquid pool here. And if we assume we inject at 80% quality and steam chamber doesn't condense any steam and we stays at 80%, in this area we are at 80%. So that means if we draw the line of 80% quality, it happens to be here for that 200 Celsius injection. Then what happens? If we go from injector towards the liquid pool top, then what happens? The quality dropping till we get to the liquid pool. At the top of the liquid pool, there's no quality. Everything condensed by that time. So in here, quality is 0. So we are at the blue line. We are at the water line. As we go inside the liquid pool, we are outside this pH diagram. We are in the liquid limit region, but we have a drop in the temperature. The subcool at this point, reservoir subcool I mean, is a temperature change from this gray point to this blue point, from this point to this point. And this governs a lot of things here, and which indirectly governs, and we're going to talk about those. So let's talk about the liquid pool interaction with the producer. So we know now how to manage the subcool, but what's a subcool? How we can use it? Is it provide us higher rate, less rate, and then we talk about flashing. So a lot of people talk about SAGD gravity drainage mechanism, and they think that SAGD is all gravity drainage, and that's true. But we should know that we have two jars. One jar is a blue jar. That's a gravity mechanism that happens inside the reservoir. It happens here. But we do have a green jar. And the green jar happens to be here. The liquid sump happens here. And producer only see the liquid sump. Producer doesn't see what happens beyond here or inside the reservoir. The producer mainly see the liquid pool. And he has to interact with the liquid pool. And this environment is dominant by pressure derivative mechanism. We have gravity drainage here, but it's very tiny compared to the pressure. So this is the whole equation. They've been like 3 years old now. They've been published in this paper. There's a series of these papers, part 1, part 2, and part 3, talking about different aspects of SAGD liquid pool interaction. But the equation here doesn't capture anything about flashing. It's been modified during these last 3 years, but the basis of this equation haven't been changed. And the base of this equation is the rate is a function of delta P drawdown and the subcool, and the temperature gradient across the liquid pool. Temperature gradient capture the heat transfer, subcool capture the operation, and delta P is also the operational constant. So it's a long equation. It becomes longer even now, but it's captured that mechanism. And before going further, you want to test it here with one field data. It happens to be one PCV pilot and one asset. And then they did a very neat thing here. They put 4 compartments, and every compartment they put a gauge for pressure, temperature, and we also put a valve. So these valves are not on, off, low. These are on and off. So they're binary, only have 2 applications. You can close it, open it. And then by closing, for example, you want to see how the zone 1 is behaving, and then you close all these zones, and you open this one, and you can see the IP. You can see the PI of that zone. You can see the SAGD behavior of the PI. And we use that data to compare with our liquid pool model here. So these are the shape of the PT gauges, and this is the production valve, and this is the valve thing, open and close. So these dots are major field data, and these lines are calculated based on the equation I previously talked about. And there are three things you can see here. First of all, as you go lower pressure, these dots happens to be tending towards another curve, and we call it flashing curve, which we're going to talk about further on how to calculate it. This line is not capturing anything about flashing at the moment. So then we're going to talk about this, how this flashing curve happens. The other thing is they never reach zero emulsion rate, which happens to be in all the PIs that we're using, Joshua, Babu there, for conventional basis. There's no delta P, there is no rate. But this is not what happens in SAGD. I talk about this is a pressure gradient system, the liquid pool, but it has a slight amount of gravity effect. So this is what happens. If you have no delta P, you see you have some gravity and you have some rates happens to be. And the other thing is capture here is higher viscosity, less rate, lower viscosity, higher rate, and that's happened to be the temperature dependent is also captured in this chart. So let's talk about a straight line because we have a straight line now, straight line PI or IPI, and this is very common in conventional world, but different formulation because there's a different system. But the basis of both are the same because both of them relies on the Darcy law, and they rely on single incompressible liquid. It happens to be as initially the conventional reservoirs were not below bubble point, a lot of them. As the time go and they go beyond the bubble point, they see, oh man, this straight line doesn't work for them. And they come up with new type of IPR curves, and the first person was Vogel. It's been used from that timing in the conventional world quite enormously. And this only relies on empirical formulation and try to capture this curve. And so there's no physics behind it, but it's captured the data really nicely. So we should have something similar to this for our SAGD curves. So similar behavior that we're trying to see here, but we go based on the physics and calculate the actual curve. So what really happens in both conventional world and SAGD, you have a single phase environment, which we call an on-flash, and then we have the flash zone, which you are coming from the red perm of 1 for liquid to some numbers lower than that. And that's a flashing effect. It can be gas liberation in conventional world, or it can be a steam coming in our reservoir. Why is that important? Because FCD is all about flashing. Inside of it, outside of it. So if you have more steam coming into FCD, that behaves different. So, but a lot of people nowadays talk about FCD flashing, and that's the flashing inside FCD. But we do have huge amount of flashing happens outside FCD that also have to be captured in our modeling and design. So let's I initially talk about what is FCD, flow control devices, and the simple one was restriction type, and they getting more, the people who operate get more interested as they go. There are different types, but all of them really doing the same thing with different type of shapes. And in basics, we have two sort of FCDs, ICD, OCD. Inflow, outflow. So in outflow, that happens to be injectors. You inject through these FCDs or through these nozzles or whatever you call it. In ICD or inflow, it happens into the producer. You put this, and the flow coming into your tubing or into your liner pass through these nozzles. So the pressure drops happens at these nozzles here and there. So in this restriction type, a lot, like more than 50% of the flow control devices these days is based on the simple equation based on the Bernoulli. But Bernoulli principle, we say the pressure plus density times V squared is always constant. And this here, we have a larger area, and we go to the smaller area. As we go through the smaller area, the V is increasing, the velocity is increasing, because this term have to be constant. This pressure drops crazy because we have a V square here. So what happens? Venturri is the same, a type of nozzle, but it's a fancier, and it got the shapes that follow the shape of the velocity here. But it happens to be the same. So the P upstream of the pressure drops at the lowest point at here, they call it throat, and then recovers some of it. And that's the delta P we are dealing with in these flow control devices. But in SAGD, because of the different temperature across, we get different temperature and the temperature getting closer to the saturation point. If you are high subcools, you don't see that effect. Nothing's changed. But at lower subcools, as the pressure drops, the throat, it goes below the saturation pressure. And what happens? Flashing. So it happens to be the compressible line. We do the CFD modeling, everything based on this. And we have a blue line. But if you put it in the SAGD environment as a result of flashing, then you push here. You got more choking happening as a result of this flashing. So this is kind of these days it's been captured. Most equations are trying to capture it as a result of empirical testing, CFD modeling, which is very hard to capture this, but they're trying to, they come up with this FCD coefficients, which is function of Reynolds, that's the same in conventional world, and also function of how much amount of temperature you are close to saturation point. So, but we have another sort of flashing that's really important, and sometimes more important than what happens inside the FCD, and this is flashing. So if you have a temperature gradient that starts a liquid pool, assuming this is constant here, constant derivative happens, and it's true actually. And as a result, we have this saturation pressure, red one, as a result of the temperature. So if you go below this pressure, you start having flashing. And this is a true pressure profile from the liquid pool to the producer. And you see at the zones close to producer for this specific case, if you go below some pressures, for some subcools, you go into the region that you have flashing. And this flashing is changing the rail plan as we discussed, and that causes a lot of things. What flashing does, what we capture, that's a picture here we're going to discuss. If you have steam bubbles as a result of this flashing, so the water vaporize, so rail plan is dropping. We also have some gas bubbles coming into the bitumen. In this study, we're not capturing this, but there is another study we capture. The reason we're not capturing it in this format of calculation in the software is because the GR is small in bitumen, and the bitumen is quite high, and the solubility is not that high, low. Solubility is pretty low, and you don't have enough timing for these gas bubbles to come out of the solution, and they create type of the foamioid that you have to capture. It's not a huge rail bump shift, it's like expansion of the bitumen shift. Let's see it here now. So this is the base of this liquid pool governing equations here. We already just discussed about this on-flash zone here and the flash zone here. We have to honor the material balance, Q up, and the comments from the on-flash zone have to be equivalent to the amount of the rate that is sucked up by the bottom part. The amount of the flashing, the dimension of flashing is important. That's the combination of temperature and the pressure. And you see everything is here at the temperature, but this delta T nu is here. It's a function of pressure calculated as sandface and the chamber. But we do have two instability to calculate when the flashing is important to capture. One is based on the derivative, the flashing zone growth, and one based on the actual dimension. You don't want the flashing based on this mechanism called negative. And it's obvious that instability 1 happens first because derivative starts to go faster than the actual value. But to get to this picture, that's this graph, you have to do a lot of heat transfer calculation and run it for several minutes. And then as a result, you get this. Softwares don't have the time to go through this for one grid. And so as a result, we have one shape of the new IPR curve, all right, as a result of this true analysis. It comes up and goes down, and this is instability 1, and this is instability 2, and you think that you go instability 1 here. But there are type of curves created in this study that you can go for more detail of what is really beyond these two equations. Coning 1 is a purple one, and coning 2 is all rely on competition between the mobility phases, and that's the steam and water. And they try to capture heat transfer, but they don't go instability criterion. They assume you know the instability criterion, and you don't have this jump. This jump happens here on the coning 1, and this is the coning 2 is very smooth to capture the physics, but not causing any convergency. But there is a test passed then by Petro-Canada Hangingstone. That's a long time ago. Initial stage of flashing comes important for recovery phases. They did this core sweeping thing, and they changed the pressure across this core. And so at this point, the temperature is the same, but they drop the pressure, and they cause the water to flash, and they see huge recovery happens in the bitumen. So this is a positive thing once you want to sweep. But we see that the instability of this pressure reduction and causing the flashing is huge and should be considered in coning also. And this is more captured by coning 1 really, but tells you that instability is enormous change, causing enormous change in its behavior. That's what we'd see in the core. This is a positive effect, but we should see the negative effect also around the liquid pool. So this picture is also talking about how we capture from pure flashing to pure instability. There is the omega in the model. You can change it as you want, from 0.9 to 0.999, whatever, not 1, anything less than 1. As you go close to 1, you're trying to capture more instability. So this curve really showed the O rate as a function of subcool. So there is an onset of subcool for the same delta P that caused instability to start happening. But if you go pure flashing, you see it's smooth. It's not changing massively, the O rate. But as you go to instability mode, it goes more and more. And in this curve, it's the same type of behavior for 0.98. This is what's suggested by us to use in most of these models, because it's not pure instability, it's not pure flashing, it's something. And we think that 0.98 represent more, but it has to be hysteromatched based on the field data. And you have that capability in this model. And the temperature gradients is a natural behavior of a reservoir. And you see in the higher temperature gradients, high heat transfer systems, the onset is not changing that much, but that for the subcool that is start changing the enormous change happens to be at the lower subcools, higher subcools for the higher temperature gradient. Last, I want to thank all the vendors that provide their performance chart, that provide the pumps data for us to do this modeling, and also thank operators which provide our data for us to verify our models. I also want to ask people for more vendors to provide more data on the pump and FCD for us to have the huge library in our models that be capable of doing all the cases for all the operators.